senior applications engineer, and it's really been a pleasure of my career and my life to work with Scott and PI. So I know a little bit about some of these technologies that he's going to talk about tonight. But what I wanted to do before he gets into that is some of the viewers here may not be that familiar with this particular technology. So I'm going to do a little technical foundation about precision positioning and motion control for optical systems, but specifically for fiber optics, photonics, and telecommunications. So note that UC Irvine Division of Continuing Education has courses in optical engineering, optical instrument design, not at the level of what Scott's going to present, but possibly at the level of what I'm doing here, because I taught this course many years ago. And Scott is a graduate of UC Irvine, so that's very appropriate. So I'm going to go really fast through these slides just to make sure that you get the feel of what's going to happen when Scott starts talking, and he's going to take what I'm going to show you and show how the automation has gone exponentially faster than what we've been able to do as I was a younger person doing some of this alignment of fiber optics for telecommunications even 20 years ago. So here we go. Let's see. Okay, so basically I'm going to go into 4 different sections, just fiber optic alignment and misalignment, things like a laser diode alignment to fiber optics, what is 6 degrees of positioning in some systems, and then what does a whole system look like where you have a laser diode, single mode fiber connecting to a chip, output of a single mode fiber, 6 degrees of axis positioning, and CCD camera. So all these slides are available if you want them. We'll have them on so you can just follow up on the fundamentals. So basically, single mode fiber, multi-mode fiber, single mode fiber here, all the different kinds of specifications that you might find on standard fiber optics. But obviously we're working down at in the microns of dimensions over here. So we have to align microns and even individual or small number of microns for single mode fibers. So this is what typical step index fiber looks like, graded index fiber, and again, single mode fiber. The light's going right down the center of the fiber, kind of not bouncing off the walls too much. Again, we have acceptance angle of fibers. Whatever fibers they are, they're all going to have some kind of an acceptance angle, and that is what you have to align to make sure that the light goes from the fiber into whatever you're trying to get it into, and likewise coming out, it has to be aligned properly as well. Typical misalignment things are the fiber separation and distance, angular misalignment, and lateral misalignment. So those are relatively obvious types of things. And again, what you'll see when Scott's presentation is how this happens really fast. You can see typically a transmitted fiber and a receiving fiber here, and there can be light loss. Easily there can be a lot of light loss if you don't have the right core diameters matching up to each other. Same thing with a waveguide to a fiber. Different fiber tips, fiber flat finishes, round finishes, angled finishes, ultrafine round finishes, all these different types of things that people do help get the light from one fiber to another or from one fiber to a device or in and out. These things, Self-Foc lenses, if you haven't heard of these are very special gradient index lenses which help you get the light in and out of fiber optics in different waveguides. So I think the next slide shows a little bit about what GRIN lens, graded index lens fibers with different pitches. The pitch has to do with the length of this glass rod, which has a radial changing index from the center outward. And so here's like a long one fiber coupled. There's many different versions of these. They've been around for several decades or more and used for fiber optics. So some of these are built into automated systems, but I like to just help people see what happens for individual fibers and what are the details. Here's just a lens, an aspherical focusing lens, getting light out of a laser into a fiber optic. You do have single mode fibers and multi-mode fibers, so that's another way. Here's a laser, just a regular laser, any kind of laser diode, a prism, a mirror, just bulk lenses here, mirror, fixed lens collimator, and now it goes into the fiber, single mode fiber, and then you look at the power meter, and find out how much light you're actually getting from the laser through all these bulk optics, through a fiber optic to the power meter. So this is just a very macro version. This was basically from 2013, some years ago. But what you'll see when Scott's presentation is this whole process has been highly automated real fast. Also, in addition to single fibers, there are arrays of fibers. So these are fibers, and then these are collimators with those self-lock lenses perhaps that are in each one, all very highly precision aligned dimensionally along the array. So these fiber grooves are very well aligned, high accuracy, probably micron or submicron level accuracy of these grooves. So you just put the fibers or the grid lenses in there, and the fibers would be mounted in these connectors. So you'll see how that works again in the high alignment throughput. Another old-fashioned way of aligning a fiber to bulk optics. OZ fiber optics, still available today. Here's just some different dimensions of typical types of mechanical devices that align optics, fiber optics, roller balls, bearings, flexures, micrometers, screws, differential micrometers, and piezos. These are all things that are, PI Physik Instrumenta is probably one of the world's leaders in this. Other companies have this type of technology available as well. And of course, many people are familiar with Newport Corporation. Both Scott and I worked at Newport Corporation many years ago. Very familiar with all these different types of manual and maybe some a little bit semi-automated, but mostly manual ways of aligning fiber optics and waveguides, laser diodes. Even back 20 years ago, we had some automated versions of these. Very nice, very high precision, but very manual. And even recently, there have been lots of graduate students, research labs using these types of devices to align their fiber optics, waveguides, silicon photonic chips, and all kinds of things. Not real easy to do. Another company, Thor Labs, has a lot of the same type of equipment that it has. These are the fiber collimators, grid lenses, different types of mechanical devices to help align fiber optics and devices. There's another version of it. Again, these are they're actually, I think, piezos inside here to do some fine alignment, and differential micrometers all built in. This is the electronic controller that they have. So all these things have been used for many years, and what you're about to see when Scott comes on is how to do it the real way. Anyway, here are some dimensions of a really alignment of a waveguide device. This could be a laser diode. So you can see there, sub-micron level dimensions that you're trying to align. And here's a typical kind of a butterfly package, a different packaging for these laser diodes. Maybe there's a waveguide in there or something, transmitters and receivers. So how do you get the fiber optic and the laser or the detector or the waveguide aligned inside this package? Of course, there's always math and physics. Just talking about the diameter of the beam. So we got to look at, what does the beam look like as it's coming out of the laser diode, trying to get into the fiber. And again, some details of getting light from the laser diode into a fiber. That's very typical. Go the other way, out of a fiber into a waveguide. And here is a little diagram of climbing up a hill of high intensity, so a digital gradient search. And Scott will talk a lot more about this in a few minutes, but just to give you an idea, you want to go to the highest intensity. How do you know when you got the best alignment of a fiber optic into a waveguide or something? By getting the maximum intensity measured at the output. So, and this is a device that was available clearly over 20 years ago in order to align in 6 degrees of freedom a waveguide, multiple fiber optics going into a waveguide, get the detector and detect the light coming out. And you can go do a scan, an angular scan around the tip of a fiber in order to continue to try and optimize the position of the fiber with respect to the waveguide or the laser diode. And here's a little diagram of an array. These are array waveguides, how you get the light, make sure you get the light into each fiber or each part of the array. How do you get the light in? How do you get the light out? Make sure it's maximized. And these are a couple pictures of some systems from probably about 15, 20 years ago that kind of show what I just showed in the demonstration, in the slides. This is actual photographs of these types of systems. There's an IR scope there. You can see people would have to use an IR scope to see how things are actually aligned because light is typically infrared. Another version, there's 2 of these hexapods. Each of these has 6 degrees of freedom, trying to align waveguides and arrays in 6 degrees of freedom in and out. Very challenging stuff. Here's another version. This is a 3 degrees of freedom, X, Y, and Z in micro positioning, micrometer resolution with these devices. And then this device, a nanocube, has 100 by 100 by 100 microns of precision to nanometer accuracy. So you can then take the light out of the fiber and get it into a detector. And here you see you get the peak intensity. This is called cyber aligner, and this was kind of the beginning of what Scott is about to show us. Same kind of thing here, trying to do nano positioning with micro positioning in order to get the optimum alignment. So there's a lot of this information on the internet, but at this point I just want to summarize again. Different fiber optic alignment requirements, fiber optics to waveguides, 6 degrees of freedom motion, and you want to get a complete system to do all this. And with that, a couple more things. AIM Photonics, that's a national manufacturing institute that's set up. So if you go to aimphotonics.com, you can learn a lot more about all these different technologies and capabilities that is available. It's kind of a fundamental national laboratory, and also there's public-private endeavors in there. And also they have an academy, aimphotonics.academy, for education. If you want to learn about it, then that information is available online as well. And now for Scott Jordan.
All right, Scott, I'm going to go ahead and make you the presenter, and then just real quick, we're going to save questions until the very end. And again, questions will all go into the chat bar. And Scott, I'll let you, once at the end of the presentation, I'll let you moderate the questions that you want to take. And just another quick reminder, please go ahead and turn off your webcam and select the option of view active cameras. So then Scott Scott's face will be on there, and as well as his presentation as well. And if you haven't done so, please mute your microphones. So without further ado, Scott, let me make you presenter.
Okay. Looking forward to that. While you do that, I would just like to say a collective hello to my friends here in this society.
Scott, we had a technical freeze there for a moment.
Yeah, I made him the presenter. Hopefully it may be just that his internet, it could be a little bit slow. So Scott warned us about this. He will come back, he'll just log back on, and then, but it should be just a few minutes. Here he comes. Scott, can you hear us?
I think I'm back. Can you hear me now?
Yes, I can hear you, Scott.
Okay. Hi, everybody. Just as I was sharing my screen, my internet died here. I've been having troubles during the day. We are now connected via the magic of photonics, tethered to my phone here. The connection will not be quite as fast as my home internet would be, but let's hope it actually works. Okay, let's start again. Can you see my screen now?
Yes, I can.
Yes.
Okay.
Okay, excellent. Murphy is with us. What can I say? Okay, let's go ahead and continue using this connection that I have. The topic of my presentation is intelligent positioning, and specifically what that means for the photonics industry in terms of increasing the efficiency of manufacturing photonic devices through automation. So just continue here. Try to gain a little bit of momentum. Okay. PI is a manufacturer of nano positioning and micro positioning equipment. We are celebrating our 50th anniversary this year. We have made automated alignment and automated optimization a very important part of the company. We have over 100 man-years of alignment expertise. Basically, there are maybe 4 or 5 engineers in the world who have led the industry, and we have 2 of them. So that's puts us in a very good place to solve these problems for our customers. We're based in Germany, but we are a global company. I myself have spent most of the past several years on airplanes, over 300,000 miles last year, going to our customers around the world, helping them do things more efficiently. Okay, we make a spectrum of equipment that we manufacture, ranging from piezo ceramics that we make to provide higher reliability and better precision and other performance attributes than any other positioning ceramic in the world. We make stages. Over the years, we've gone to larger and larger format stages. About 3 years ago, we purchased ACS, which is a very well-regarded industrial controls manufacturer. So that is PI. Let's talk about why we're here. We're here because the world's appetite for data has just been insatiable. Part of it is because we're all walking around with supercomputers in our pockets. In this case, my little pocket supercomputer is what's providing the internet now, now that we had this issue with my home cable. Just to put it in perspective, I doubt anyone 20 years ago would have said, well, what's going to be generating 16 or 15 petabytes of data every year? What application could possibly generate that? I guarantee you, no one would have said people taking pictures of themselves, but that's the case. 14 petabytes of data in 2016 were generated and uploaded just to a single application. That's Google Photos. That doesn't include Instagram, Facebook, iCloud, Twitter, all the other things. It doesn't include sharing. It's just the uploads to Google Photos. That's a pretty amazing statistic right there, and it's one that's several years old. I'm sure it's done nothing but grow since then. Over 200 million individuals upload selfies every month, and these photographs right here show you this is a highly democratized application. You have very rich and famous people taking selfies. You have people who just washed up on the boat on the shores of Greece taking selfies, all doing the same thing. So this is just one example. Here we are in the middle of a pandemic, and I am here reading about applications where researchers like 23andMe, for example, are mounting a research to take the genomic information from people and correlate it with their symptoms and their prognoses and the data, the therapies that they undergo. And can you imagine how much information is required to be generated, uploaded, correlated, data-based? It takes photonics. It takes photonics because it's much more energy efficient. It is much more capacious, more scalable. You can build a data center that's distributed rather than build up in one great big monolith. There are many benefits to doing things the photonics ways, especially regarding interconnects at this point. It is simply more efficient and takes less energy to convey a bit of information using photons than it is using electrons and shoving charge down a long cable of copper. But that's just interconnects. When you think about it, we haven't even scratched the surface of things like optical computing or quantum computing or quantum communications, all of which will depend on photonics as well. So this is just really the beginning of what I think will be a wave of photonics. So, continue. The problem with photonics is you can't just take a photonic device, as Don was describing, and solder a wire to it. Instead, the optical elements, whether they're fibers, waveguides, or diffractive elements, or refractive elements, or chips, what have you, they all need to be aligned, packaged, tested. The alignment must occur multiple times. It starts on the wafer. It starts where the devices are fabricated on the wafer, and they must be graded, or they might be validated, because costs, as you see in these pie charts here, the cost of packaging is really high. And that means you cannot afford to package bad devices. So they must be tested, starting at the wafer level, using a device called a wafer prober. And then once the devices are known to be good, they can be diced off and subjected to further testing, because it's ridiculously easy to kill these devices at every step along the way. So they need to be tested over and over again to validate that they're still alive, and then packaged, and every step requires alignment. So it's the most heavily leveraged part of manufacturing photonic devices. Now, what we've done is we've developed some unique alignment capabilities. As Don mentioned, I've been working in the field of photonic alignment for a long time. I kind of fell backwards into it back in my Newport days. Our friend Mark Bandhauer is in the audience here. He was there, and this was a very interesting time. It was the dawn of fiber optics, and single mode fibers came out in the 1980s, laser diodes. All of those things that are fundamental to what we do today had their birth back then in the 1980s, 1990s, and people had to align these things. So we came up with a way of doing that for its era was especially time efficient. But today, the devices have changed. Today, they're being made on wafers. That means that there are more devices per square centimeter. That means there are lots of channels, because you can build these array devices that Don was describing. And so we need a spectrum of positioning equipment to address those individual applications. There's no one size fits all. So we built this into hexapods, which are 6 degree of freedom positioners with some really nice capabilities. Our piezo nano positioners, which not only offer really high resolution that's sometimes necessary, but really high speeds, which is always necessary in a manufacturing environment. And then our large stages, driven by our ACS controls, where you can take an entire tray or an entire wafer and scan over the entire thing and select individual parts and perform very, very exacting alignment and characterization of devices over large areas, large formats. So we have lots of different bits and pieces in our toolkit that we can put together for our customers' needs. And we'll show you some of our customers' applications as these slides come along. Okay, the basic approach, the basic problem statement is that you have some sort of a figure of merit, some sort of quality metric that you need to maximize. And there may be some local maxima and then one great big peak that you want to be sure is the one that you select. So there are several things you need to do. First is to select that main peak. The second is to optimize, perhaps even track that peak if it moves around due to thermal drifts or other motions that you may have to perform. Now, this figure of merit for most photonic applications is optical power. You take your optical fiber and your laser diode, you want to bring them into a mutual orientation that optimizes the amount of power that goes from one device to the other. But it could be other things as well. For example, I'll talk a little bit further about some of the other figures of merit that we can optimize, but just say you were aligning a laser cavity and you had some measure of beam quality that you wanted to optimize. Chances are it's going to be a hill-shaped function, just like this. And we can find the peak of that with respect to the positioning of the various devices. And this is something our customers are doing today. Cameras, you may have a figure of merit that represents the quality of the image at the image sensor. And you need to align all the lenses in the lens assembly in order to optimize the quality of the image as perceived at the image sensor. So again, it tends to be a hill-shaped type function. One of the challenges that we met with the latest technology that I'm describing is that we avoided any assumptions about the symmetry, circularity, Gaussianness of these hill-shaped functions. Our alignment algorithm doesn't care. If there is a peak, it will find it. So the first tool, there are basically two basic approaches. The first is called an area scan. It does what it sounds like. It scans an area and then determines the optimum position. The optimum position can be either observed or calculated. In this example I just showed you, we calculated the position, the best position is inside the scan lines. It's in between them that we were able to fit a Gaussian in this case to determine where that peak should reside given the data that we caught in the scan there. That means we can do a fairly coarse area scan, meaning a very fast area scan, and still do a good job of localizing where the main peak is. Now that was a slow motion view. Given the internet troubles we're having, this may or may not show, but let me show you what the actual time is. There. Okay. About 300 milliseconds is typical for making an area scan over a 100 by 100 micron area for one of our nanocubes. So it's very fast. The second approach is called a gradient search. Here we make a small circular motion of one device with respect to the other, and we observe the modulation that causes in the optical throughput. So if I'm making a circle at a certain frequency, we're going to see modulation at that frequency. And that the phase and amplitude of that modulation tells us what the gradient is. And again, that was a slow motion view. The actual speed is on the order of 200, 300 milliseconds. So from a physical standpoint, this is what's going on. You saw similar Gaussian charts here, certain similar graphs in the slides that Don showed. And this shows the circular dither we're performing. Typically it's very small. It's on the order of a micron in radius or something like that. But you'll notice that at this position in the, I'm assuming you can see my cursor here. At this position in the dither, we have this much optical power or this much figure of merit. At this point over here, we have this much. So as we go around the circle, we modulate as the dither proceeds. This is a continuous process. It happens in real time. And from this information, we can determine which way is up. and follow that gradient to the top of the mountain and then stay there, even if the mountain moves around. So what's new, what's different about the way we're doing things versus some of the older solutions that Don showed you, including our own, is that we can do this in multiple elements, multiple inputs and outputs, multiple degrees of freedom, all at the same time, even if they interact. In fact, they will interact. What happens is that our controllers can take this data and unwrap all of the dependencies that are occurring, and it could do so in real time. So that, for example, one of the best examples is for an array device, where you may have some channels, 4, 16, or 20, or 90 channels, all in a row or in some sort of a rectilinear array. And you have two devices with similar configuration, and you need to align them not only in X and Y, which is very, very sensitive, but also in theta Z, so that rotate about the optical axis so that all the channels are lined up. So you can think about what the problem is in that case, because anytime, if you're not rotating exactly on the optical axis to the nanometer, then any motion in theta Z that you perform will de-align in X and Y. And that is why it takes so long to align things manually, or even in a semi-automated fashion, or even using previous technologies that Don was talking about. It's because you make a motion in one degree of freedom that destroys your alignment in other degrees of freedom, and you need to go back and fix that, and then resume your motion in theta Z. This loop takes a lot of time. Typically, to align even a simple array device, it's on the order of 2 minutes to do that. So that's unacceptable. If you have a wafer that's got 10,000 devices on it and you need to test them, if it takes 2 minutes per device, you can figure out how unaffordable that would be. It needs to be down in the seconds range, or better yet, less than 1 second, which is where we are with this technology. Now, as I mentioned earlier, the hill-shaped functionality doesn't need to be a Gaussian. It just needs to have a clear, unequivocal peak. And if you can give us an adequately fast figure of merit, because this is all about speed, we can optimize it as a function of position across multiple degrees of freedom, multiple elements, multiple inputs and outputs, and we can do that all in one step. So that's why it's so much faster. So let's talk about this. The old way of doing things is what you see here. Single threaded alignments that tended to be, by our standards today, pretty slow. What I'm talking about today is not only are the individual alignments much faster than they used to be, but we can do more of them all at once. So the overall productivity, the overall throughput of these mechanisms is just so much better. And that's why this is important for process economics. Time is money. The wafers themselves, they're pennies for the silicon, and then a few dollars for the individual steps that go into it. But the total cost is dominated by that packaging. And so consequently, this alignment functionality is absolutely key to being able to make money on these systems or on these devices. So parallelism is what we use to eliminate those loops that I mentioned before, where you have to, for example, in the case of an array device, align in X and Y, make a small motion in theta Z, go back and fix X and Y over and over again. This device right here that you see is a really interesting device. It's a chip made by IMEC, and those are 60 diffractive couplers, and hovering above them is a multi-core fiber probe using technology from Silicon Photonics, a very clever company in New Jersey. This has over 60 channels, and the pitch from channel to channel is very compressed. It's on the order of 10 to 40 microns from core to core, and very precisely placed. They could do this with over 90 cores in basically the same sort of area. So it's a very good way of saving real estate in these chips, because the more channels that you have, the more complex the chip can can be, the more functionality it can be reduced to a chip level. There's many benefits to being able to do things in silicon photonics as an architecture. So the traditional alignment loop to align something like this takes minutes, or you can do it all in one step. Let me show you. Now here I'm hoping that the videos actually show here. I'm looking on another screen here, and it does seem like it's coming up. 3 photonics wests ago, we showed this technology for the first time, aligning single mode fiber arrays. In this case, we were just using glass fiber arrays because everyone understands them. So you can see here on the screen, we do an area scan, you build a little picture of where the main mode is. We do a lock on in X and Y, and then we do a parallel alignment in theta Z. And it looks like the video didn't quite show, but let me show you another one. The next year, we had customers saying, well, what about my devices that had inputs and outputs? And so what we did is we built an assembly that had fiber arrays on the input and output. We did the same thing where we did the area scan to find the peak on both sides, and then a gradient search to lock onto them on both sides, and a parallel gradient search to perform the theta Z alignment on both sides. And again, my apologies for the bandwidth issues we seem to be having here. I'd be happy to provide these slides to anyone with the videos built into them so you can run them on your own computer. Now, the interesting thing about this demonstration with the array input and the array output, it's doing twice as many alignments as the first video that I showed you. Twice as many. The previous one was just a single array input. This one is 2 array inputs, twice as many alignments, but it takes about the same amount of time. That's because all the alignments are being performed in parallel. So the interesting thing about this technology is that the overall time to perform a global optimization across all the elements, inputs and outputs and degrees of freedom, it's almost independent of the number of alignments being performed because they're being performed in parallel. So that's what's new. Now, this is an example of what we do with wafer. This is a waveguide that we've embedded into a wafer, and you can see the alignment is being done on both sides simultaneously. It takes about 300 milliseconds. So that has been used to build a whole new class of tools called wafer probers. In the lead for that is a company called FormFactor and their subsidiary Cascade. They have based their photonic probers on the architecture that I've shown you. In this case, they're using our piezoelectric nanocube for its speed and its resolution and its ability to track all day without any wear at all. And they've mounted that on our hexapods, 1 or 2 hexapods. This video is available on YouTube if you would like to see it. I'll put the URL there. Okay. Somebody is talking. Let's go.
Which can give results in less than an hour. And that is enormously important because what we don't want to do is have hospital beds filled up with people who do not have the coronavirus. We want to make sure that those beds are there for the people who need them. And rapid processing of these tests is terribly important. So on an emergency basis, we've got to get these tests done, we've got to get the processing done, and we need to move on this as aggressively as we can. Furthermore,
looks like somebody's phone is playing a video right now, or
right. I should have mentioned at the beginning of my presentation, I have very bad ears, and it's difficult for me to understand what's being said here. Therefore, I believe Bo is going to be providing questions to me via the chat function to be sure that I get it right. So I will answer that as soon as it pops up on the chat. So.
Yeah, I think, Scott, based on what I was hearing from it, it sounded like somebody had a video going on in the background and didn't mute. So I think I don't think it was a question. So I think it's over now. So I think you can go ahead with your presentation.
Okay, all righty. So anyway, I highly recommend, even if you don't have any interest in wafer probe, that you watch that video that FormFactor has put up on YouTube. It's really informative and frankly, amazing to watch. So FormFactor has, they're just one of the players in the field, but they're miles ahead of anyone else at the moment. And this is an example of one of their edge coupling setups. They have a new brochure that's very impressive, very informative about the role that wafer probers play in silicon photonics. And it's really every silicon photonic device meets a wafer prober when it is freshly constructed. Here's something interesting. This is a FormFactor prober looking at some wafers made by a company that that I know pretty well. I've been watching here in Silicon Valley called PsiQuantum. PsiQuantum is doing some really interesting stuff. They have been a stealth company for a long time, and quantum computing is seeing some significant investment from the big guys, people like Google and Microsoft and IBM, and the major universities have been pursuing quantum circuitry that could be used to build practical quantum computers. So they just recently have shaken off their cloak, and they are now talking out loud about what they're doing. And it's a big deal when an IBM or a Google creates a computer with 25 or 56 qubits. These guys are talking 1 million qubits. So that changes the game entirely. And anyway, so there you go. The interesting thing about this is from their website. You see right there, that photograph that I posted on LinkedIn. It was part of several articles that they've been featured in. That's a wafer prober. When do people do wafer probing? When they are going into manufacturing, when they are actually making wafers and cycling them through. And maybe they're production prototypes, but it's getting very close to being a product, which tells me quantum is real. It's not something our great grandkids are going to see emerging 100 years from now. It's not science fiction. It's here and now. And there's the proof. Wafer probers, probing actual wafers with devices on them. And that's pretty stunning. Here's another quantum application, one of my favorite slides. Here we had a customer at Purdue University. They're looking at quantum emitters, single photon emitters, emitters that don't bleach with time, emitters that emit fully randomized photons that are not correlated with respect to each other. These are very important properties for a quantum emitter that is supposed to generate photons that can be used for quantum computing, quantum communications. What these are atomic level defects in diamond crystal, where a carbon atom has been replaced by, in this case, a nitrogen atom, or silicon is another one. And other crystal lattices also show problems in this way. So what they want to do is take a microscope slide with some diamond on it, diamond dust or diamond films, and then scan that slide until they find little atomic scale defects that fluoresce under a specific illumination with laser. So what they did was they took one of our piezoelectric microscopy stages and they connected it to one of our alignment controllers. Then I flew in and visited with them, and we figured out how to make this work. What you see here, this blue screen that you see, that is an area scan. It's several tens of microns in span and very, very fine submicron pitch of the scan lines. And you can see that as it scans in this arrangement here, as it scans, it identifies these little glowing elements. Those are atoms. And the way I wrote the software is you can click on one of those atoms of interest, and it will automatically lock onto it and track it using the gradient search that I described earlier. The key about that is that the dither radius is on the order of maybe 5 or 10 nanometers in this case. So it's a really small, very fine dither, and yet we can track it. We can track atoms. So that kind of gives you an idea of how this can scale. What I would like to do now is be very brave and move over to my demonstration PC. And here, Bo, if you could make the PI computer a presenter, I will show you. This demonstration is running on the desk right next to me.
Will do. I'm doing it right now. So make present.
Okay.
Okay.
Yeah.
PI is now.
Here we go. All right. Got it. Okay. Now we have the same bandwidth constraints here that we have on my presentation computer, but let me describe what's going on. You see a screen with a bunch of buttons, something I threw together in LabVIEW. In the background is a Python script that is pressing the buttons of to repeat a process over. Gradient search is performed in parallel on both sides. So you can see in a couple of seconds, we do what would take several minutes to do using older technology. This is very much live data. So I'm going to stop sharing that screen and go back over to my PC. And Bo, if you could switch over the presenter to my presentation PC, here we go. All right. Okay, so now that takes me to my concluding slides. So this is an example of something our customers use our hexapods for, building smartphone cameras. And several billion smartphone cameras are made every year. I mean, my phone has 4 cameras on it, and they need to be assembled, and they have multiple elements, and they get better every year, which means the tolerances get better and tighter. The imaging sensors get better. Certainly the software grows more complicated as well. So what people use our hexapods for is to have one hexapod per element that needs to be aligned, and they have been doing these alignments one element at a time to optimize the image at the image sensor. And that takes time. But what we have recently proven they can do using these techniques is take that image and do the alignment of all the elements in multiple degrees of freedom at the same time. And that is a big time saver. And considering that smartphone cameras are being made by the billions every year, billions with a B, this is an example of where we can really save our customers some money. Also, laser manufacturing. Lasers are pretty complicated these days. They have diffractive elements and definitely reflective elements, gain media, and they all need to be aligned with respect to each other to optimize some figure of merit. So this is where our customers are using this technology as well, outside of Silicon Photonics. Here on this screen is my last slide, and this shows you on the left is a complicated system you see us assembling for the big laser conference in Munich last summer. Here we had three nests with devices on it, and the system with that big gantry would shuttle from nest to nest, just as you would do in a typical manufacturing situation where you would have parts being picked from trays and placed in various fixtures and being subjected to gluing and inspection and validation and things of that sort. And now the alignment is really the least of it these days. It's because it takes so little time. These applications now tend to be dominated by glue curing and things of that sort rather than alignment. So that's quite a contribution. On the right-hand side, you can see my original proof of principle for the camera alignment, where I took a couple of lenses and put them in some fixtures there. Each of those is mounted on a hexapod. And there's a card that's a knife edge that you can see. What we're doing is we're taking the images frame by frame and performing a 2D Fourier transform and trying to optimize the high frequency component of that. So doing all that, and we're done. So less than a second to perform a multiple degree of freedom alignment of, in this case, 2 lenses, but could be any number. And that takes me to the end of my presentation. The takeaway here is that we're going to be seeing more and more photonics as time goes on. The presentations like this, these telepresences that I think are going to be a permanent feature of business from now on, they're enabled by photonics. The streaming media, the Netflixing and Netflix binging that you've been doing during our lockdown, that's all enabled by photonics. And just more and more of that. Personalized medicine, the new kinds of diagnostics, telemedicine, photonics is the enabler of all these things. So you're in an important industry, and a very diverse industry with lots of different applications that can benefit from this new type of intelligent positioning. The way I like to describe this is, before, positioners would do what you would tell them to do. You would tell them, go to point A, now go to point B. And the degree to which they achieved your command, the precision, the repeatability, those are all measures of obedience. The more obedient positioners, the nano positioners, for example, are the ones that you can tell them what to do and they will do it. They will go to a commanded position. But that typically isn't what you want to do. You typically don't want to do positioning. You want to do optimization. You want to build photonic devices. You want your laser to be optimized so that you can glue everything together and ship it out the door without having to spend days of labor trying to get everything aligned. So this optimization is what you want to do. And now with this new technology and this new field of intelligent micropositioning, we can help our customers do that so much more efficiently and so much lower cost than could otherwise be done. So I hope we can all keep in touch. You have on the screen here my email address, LinkedIn, WeChat. WeChat is, if you haven't heard of it, it's what people use in China. And I've been spending quite a lot of my time with our customers in China and elsewhere in Asia. So I've learned over time that if you want to do business in China, you must have a presence on WeChat. So that's what that's all about. And LinkedIn, of course. We have a tech note that I'd be happy to send to you as a PDF on practical examples of how to use this parallel stuff. And it really boils down to look for those loops where you do an alignment, then you do a different alignment, then you have to go back and fix the first alignment, and over and over and over again for several minutes. Those loops are what you can attack with this technology. Do it all at once instead. So that's what I have to say. Thank you very much for your audience and for your attention. And I should look at the chat here.
Yeah, please send in your questions. Thank you so much, Scott. And we're opening up for questions. Please send them in through the chat bar. I believe there is one question that was posted.
There are any questions? Okay. So, yes, do you solution integrated? Okay. I'm reading one for typically include integrated optical sensors for evaluating the cost function of the alignment routine. They can. Very often we make a power meter, an optical power meter. It's very popular for these fast, high-speed applications. It's really high bandwidth. It's optimized for this type of application. You'd be surprised how slow many power meters are. I've worked with some where customers have said, I have the power meter, let's use this. And I'll try it and find it has like a 2 hertz analog bandwidth. And then they'll look at the manufacturer specifications and they say, but it's 100 kilosamples per second. Well, yeah, you can rapidly sample a slowly varying signal. And unfortunately, most power meters are kind of slow. There are a few out there that are fast enough to keep up with this system. One is ours, another is the new Focus 2101, 2103 power meters, very fast. There are some others, some Keithley's and Keysight that in some models are fast enough and have the type of interfacing that we need. So we can use devices that have their own built-in photosensor. We can just take a photocurrent. We have one customer, this is a great story. We had one customer that we were working with here in Silicon Valley, very big customer, very, very big producer of Silicon Photonics devices. And we have worked with them throughout the prototyping and design of their devices. And we were using an analog tap that gave us a photocurrent from a monitor photodiode inside their device. Well, got a call one day in a panic. The device was going into the next phase of production prototyping, and the analog photocurrent tap had been removed. And they were going, what do we do now? And I said, well, you have some way, the photodetector's inside, right? Yeah. Okay, is there some way of getting to that photodetector? And they said, well, yeah, we have a received signal strength indicator, RSSI. We can query that over I2C. I said, great, okay, that's fine. I'm going to go away, come back the next day. So I went home, same laboratory here, and built an Arduino, programmed an Arduino, a little microcontroller, $12 off of Amazon with a little DAC chip to query the RSSI port. And what comes back is a number. And the DAC, it would output that to the DAC, and the DAC would create a voltage that could be used as the figure of merit for our systems here. And by the way, if you see me looking out of the window right now, there are about 8 police cars and ambulances and fire trucks down the street. I've never seen anything going on like this in my neighborhood. And I think a hearse just drove up. Well, okay. Anyway, so we live in weird times, I tell you. So that was an example of creating a figure of merit using a calculation, using the microcontroller as a protocol converter. And it worked really well. I could do that protocol conversion about 3,000 times a second, which is fast enough for me. And that went into production. That customer now has over 3 dozen applications, 3 dozen workstations building these products for 4 years now. And that has worked out very well for everybody. So yes, we can do all of that. Let me see here. Next question. Anyway, Dominic, I hope that long-winded answer gave you the reassurance that you need. Yes, we can use whatever signal might be available. Okay, so from Andy, okay, no, this is from Ramirka. Are there services one can purchase for small fiber component alignment in the 2.8 to 4.8 micron wavelength? And the answer is, yeah, we just need fast metrology. That could be a problem for those longer wavelengths because they use thermopile detectors that can be slow. So we would want to try to optimize the bandwidth of the metrology, but we don't care about the wavelength. All we care about are the optical physics, this hill-shaped optimization function that just about everything we see has out there. So yes, the answer to that is sure. It comes down to the question of what metrology you use and how fast can it be. So from Andy, FIO command works for 2 axes, but how do you do the other angles? Oh, okay. Well, FIO command, not quite sure what you mean by that. That might be a reference to one of our older instruments that had a command, I believe, called FIO. This new technology, the way we would do other angles, for example, well, I've told you how we can lock it on with in X and Y with a gradient search that runs continuously on one channel of an array device. And then we could do another independent alignment in a different degree of freedom. That can also be gimbaling type angle motions. We don't care. The XY keeps everything locked on. So your rotational center point does not need to be perfect. Any parasitic motions caused by the other angular and other degrees of freedom alignments that you're performing are automatically unwrapped because of that lock-on process. So let's see. So could you explain let's figure this out. Okay, the best way to explain it is to consider you have a positioning device that is precisely aligned to the optical axis. So when I rotate, I'm rotating about that optical axis. Now, achieving that with shims and maybe telling our hexapod exactly where to put things, you'll get close, but you will probably not get exactly on the optical axis. With this technology, you don't care, because we can lock on to that optical axis using the XY gradient search, which is very fast. And so it can compensate in real time for any misplacement of the rotational center point, which means we can perform the full 6 degree of freedom alignment in several independent processes. So there's an XY process, there is a theta Z process, there may be a gimbaling process, and there could be a Z process as well. If it's a lensed coupling, we can find the beam waist using a gradient search in Z. And these can all operate at the same time. Now, that's the key, is this parallel actuation of this technology is something that was not possible before. Okay, so I see the measurements are in GUI, or GUI or in LabVIEW. Why? Because I'm an old fossil, I use LabVIEW. Some of our customers, we have a software stack that we ship with each of our equipment. You can use LabVIEW. There are really good LabVIEW libraries. That's what I tend to use. There's Python, there's C#, there's C++, there's Delphi. We still have customers who use Delphi. I'd say the most popular is probably either Python or C#. I use LabVIEW because it lets me make pretty graphics, and I've been using it for 30 some odd years. I can program a LabVIEW GUI very rapidly, and so that's why I use it. You don't have to use it by any means. By the way, all of our software library is platform agnostic. In addition to using whatever programming language or development platform you want, our libraries are consistent across Windows, Linux, and macOS. We have customers using each of those, and the software is the same. The libraries are exactly the same. The documentation, which is very comprehensive, is exactly the same. So that's why LabVIEW. Okay, Joseph had a question. I'm confused as to how the loop optimization works. Is the optimization? I'm not by the bandwidth. It is. Can I push a rope? If the stage is slow, then you can't do fast things with it. That's why we use the nanocube. The nanocube is a device with 100 microns of travel, X, Y, and Z. We also have an XY one, and very, very fast. Typical resonant frequency of a nanocube with a typical load is in the order of several hundred hertz, which means the positioning bandwidth is typically, rule of thumb, about 1/3 of that. So if we have a 500, 600 hertz nanocube, that means we can do these little circular dithers well over 100 hertz. That's fast, especially by alignment standards. So the bandwidth of the positioning devices is definitely a limiter. Physics is physics, but we get around that by using things like piezoelectric nanopositioning for the highest bandwidth requirements, which is typically the tracking. The XY is usually the most sensitive and the most compromised by motions and other degrees of freedom. So that's typically where we use the nanocube. You don't have to. You can do it all with the hexapod, but the nanocube really speeds things up, and most of our customers are really into saving money in their production. Time is money. Okay. So let's see. Read the next one here. First opportunity to attend a meeting. Very good, Tom. Good to see you. The parallelism aspect, Joseph mentions. It's not quite a question, but the parallelism is really the thing that people often have trouble understanding. And the way to simplify it is to say, okay, an array device. And I keep coming back to array devices because they dominate silicon photonics today. So this ability to align multiple channels and get them all lined up so the full array device works is really important, and also really painful in previous technologies, previous implementations. So this ability to perform, well, what we do is we divide the challenge into bite-sized pieces. You have this array that needs to be aligned in multiple degrees of freedom. Break that down. You have one process that's in X and Y. You have another process that's in theta Z. You have another process that maybe dimpling is important for your application. You might have another process in Z. If it's a lensed coupling, you want to find that optimum point in Z. So that's 4 processes maximum per silicon photonic coupling, array coupling. So those 4 processes, you define them. You tell our controller, I have an XY process. I'm going to call that process 1. It's these mechanical axes looking at this optical interface, and then that's process 1. You've now defined process 1. Process 2 might be this theta Z motion here, which mechanical axes does that involve? What optical interface do you want it to pay attention to? If you have 2 channels, you might want to pay attention to the second channel to optimize it. So now you've defined process 2. And similarly, process 3, maybe process 4. Now you've defined the processes. So we give you a command called FRS, fast routine start. And you can issue that command FRS 1, 2, 3, 4. And the controller will automatically execute all those processes simultaneously in parallel. So all you have to do is take your application and divide it into processes, and then we take care of the rest. It's all built into the controller, so it's really fast. Okay, let's see. Maurice had a question. When you talk about optimization using parallelism, is that achieved because you are scanning the space using an array of detectors versus a single detector? No, not necessarily. Consider the case where you have an array device. If it sounds like I'm stuck in the groove, that's because it's really important to the industry. Very often, about maybe 40% of the time, you will get an array device where 2 of the array elements are connected in a U. They're connected together. These have various names. I've heard them called omega devices and things like that. It's basically 2 of the channels are dedicated to alignment. So light goes in one and it comes out the other. So there's only one detector. One source comes through, one output. So now I need to align in X and Y and theta Z at a minimum to line up that array. But I only have one detector. That's okay. Our system looks at the modulation caused by both of those processes and separates them. It's automatic. The physics behind it is deceptively simple. It's one of those things where when people see what we're doing at a low level, they go, "Oh, why didn't I think of that?" It's really very, very straightforward and easy to use. So I hope that answers your question. It's just one of these things where if we perform training seminars for our customers, and we're going to be doing a lot of that remotely in the next few weeks. And we walk them through this taking an application, dividing it into bite-sized pieces, and then running whichever pieces they want in parallel using the fast routine start command. And it's the same for all of our implementations, hexapod, nanocube, it's the same commands. So independent degrees of freedom, right, exactly. Do you have a process or device to quickly align polarization into a polarization maintaining fiber? Yes. Couple of ways of doing that. First, there was one application where we had an output from a polarimeter, an instrument that would measure the polarization vector and the amplitude. And it was a hill-shaped function that when the rotation was correct, the physical rotation of the elements, then the polarimeter would be peaked, and that's what we needed to determine the correct rotational orientation of the devices. So yes, if you give us metrology, again, if it has some sort of hill-shaped figure of goodness that gets better and then gets worse, we can find that peak and we can track it. So polarization is just one quantity that can be done in that way. Okay. Rimmerke has, can the multivariate optimization include non-geometrical parameters like temperature, polarization, and spectral components? Interesting question. We make positioning equipment, but you could be varying those other quantities at the same time and looking for their optimum independently. In a way, this happens every time someone turns a laser on in one of our devices, one of their devices. The laser creates heat. You get things moving around. I mean, imagine those atoms in that quantum application. There's an enormous amount of thermal drift that occurs when the system has been illuminated by laser over a period of minutes, especially considering the scale of the devices that are being aligned. So we can track that even when you are changing the external parameters. In wafer probing, very often engineering wafer probers, as they're called, from people like FormFactor, there are others out there as well, MPI, Semiprobe, who build systems like this. But FormFactor has a very advanced thermal characterization system that heats and cools the entire wafer or parts of the wafer to test the components under different environmental conditions. So there's an example of a multivariate alignment occurring in parallel with physical changes in the system in order to determine the characteristics of the device. Okay, let's see here. We have more. Polarization multivariate. From Mark Bandhauer. Hi, Mark. Thank you. Okay. Yeah, was manual labor. Mark was reminiscing about how it was back in the old days. At the beginning of our careers in the late 1980s, 1990s, the key word was single mode fibers were starting to get really exciting because people realized you could send signals uncorrupted for miles and miles, and so that, I don't know if anyone in this audience besides me is old enough to remember what a long distance phone call used to be like. There were delays where you'd say something and you'd have to be patient for your voice was bouncing off a satellite to whoever it was you were talking to. So you were talking 50,000 miles of traversal at a minimum. And this took time and capacity was limited and it was expensive. Boy, my mother, if you said, can I make a long distance call? She'd go white in the face. It was expensive. So that all changed. That all changed because of photonics, because we replaced those satellite links with transoceanic and transcontinental links of optical fibers. That was the first big application for photonics. It was a single application, and that made it vulnerable. Eventually, they laid enough fiber and enough repeaters across enough oceans to satisfy demand for long-distance telephone calls for the next 10 years, and the industry basically shut down. Today, I don't think that's going to happen because we have so many applications, streaming media, social networks, personal medicine, smart cities, smart cars, autonomous vehicles, all the stuff that we've talked about, selfies. And so, yeah, so I don't see that changing anytime soon. Okay, the last alignment, about 300 milliseconds. This is Dominic. Was with the nanocube. Yes, it was. But the parallel approach will save time even for a slower positioner like a hexapod. Yes, it will. Definitely will. It's typically at least an order of magnitude faster, typically 2 than the old way of doing things, even for a slower positioner. So yes. Can you give me a ballpark time for a 6-axis alignment? It depends a little bit on the devices. It depends on the metrology, but 2 seconds maybe, something like that. So it's on that order. We're not talking minutes anymore, that's for sure. What is the limit on theta clocking? This is from Maurice. I'm not quite sure what you mean by theta clocking. If somebody could throw me a clue. What is the limit on theta clocking? Well, the theta travels are limited by the devices. For the hexapods we show here, they're typically on the order of plus minus 15 degrees, something like that, something on that order. Goniometers can be used to give you more rotational travel in theta z. So it depends on your choice of devices, if that's what you meant. Okay, let's see. From MS, if your sensor is something like a CCD and the hill shape occurs over only a few pixels, how do you resolve subpixel accuracy? Interesting question. It comes down to how do you calculate the figure of merit? Can you process those few pixels in a way that gives you that hill-shaped figure of merit? If so, and I've done it with that sensor I showed you in the previous slide. It was a cell phone sensor made by Omnivision, I believe, and I was able to clock that at 260 frames per second and perform a 2D Fourier transform. I was doing all this in LabVIEW, of course, because that's my fate. And then that generated a figure of merit based on that calculation. So our system doesn't care. If you give it a hill-shaped function of some sort, it will find the peak of that hill. The only requirement is it needs to be fairly fast. If my frame rate were 10 frames per second instead of 250 or 260 frames per second, that would bottleneck some of my processes. The conclusion might be I wouldn't be able to do as much in parallel as I could with a faster frame rate. But if you're only talking a couple of pixels, and if you have some way of teasing out a figure of merit from just a couple of pixels, it's going to be some sort of calculation, I'm sure. As long as that calculation can be performed quickly enough, we can use it. So, Joseph mentioned, I think he's reading off an analog power meter. I am in this case, my demonstration that I have right here. That is actually the most common configuration. But as I've described, you have to think outside that box. There are other figures of merit that our customers are optimizing every day using slow, incremental, looping ways of doing things. We can fix that. We can make it much more time effective. Okay, CCD cameras are quite slow. Are you perhaps using a CMOS camera? I have no idea. The camera I bought was off of Amazon, has a USB 2 connection, and I was able to clock it at 250 frames per second. That was fast enough for my purposes. In fact, more than fast enough. I could go down to maybe 30 frames per second and still be able to do most of what you saw in that video. But the faster is always better. Faster means more things done at the same time. The more speed that you can give me in the metrology and that figure of merit, the more I can do in any given millisecond. So let's see. Thanks for organizing the event. Well, thank you for having me. It looks like we're running out of questions. So, Bo, I guess I give it back to you.
Yeah, thank you so much,
Thanks to
Scott.
everybody for your time.
Yeah, no worries, Scott. So thank you so much to all of our attendees for asking such great questions, and also for staying around and also joining us in this presentation. As normal, our tradition, if we were physically, we want to offer you a 1-year membership to the OSSC to say thank you. We normally have a plaque in which that we would, give to you, and we'll take some, very nice pictures. But unfortunately, that's our situation right now. So there have been some people who have asked, and I believe you said you would. Can we put your slides on our website in order for them, anyone?
Happy to.
So we would love to do that. So for those who are interested, please go to our website and you'll see and we'll post them on right now. So thank you so much, everyone, for coming. Thank you so much, John, for organizing this event. Scott, go ahead.
I just wanted to say, I sent you some draft slides the other day. Let me send you the final slides as presented.
Gotcha.
I'll try to get those. I'm at the mercy of the bandwidth here, but I will try to get them to you tonight. Okay.
No worries.
Thank you, everybody.
Scott, I can't say enough to thank you again, so I just want to say hi to all of my PI buddies, okay, when you see them, and hopefully I'll get to see everybody again soon. Thank you, Bo.
I hope so too.
Great meeting.
And,
no worries. Thank you so much, Don, for helping putting this together. Again, thank you to everyone. Please stay safe, and then we're looking forward to see you in May. We'll have another one of these great talks, and please, again, stay safe, and we're looking forward to see you again. So I call this meeting. Thank you so much, everyone. Have a great
I wanted to personally thank Scott because I just wanted to say Scott and I on the way back to college. So so always good to see him.
Bye, everybody.
Okay. Bye-bye.
Great job, Don. Thank you so much, everyone. Yes, Don.